So hi and welcome to my session on Bulletproof Java Enterprise Applications for the Hard Production Life. Quite a title, I believe. And yeah, a session how to make our enterprise Java applications more resilient, more apt for production. Because it's, well, kind of easy to develop enterprise applications, especially if you can use APIs that make it very efficient to, implement business logic. But running all that stuff on production is quite a different story, and then you have to care about your implementations and implementation-specific details. And what I'm going to show you is especially a few resiliency patterns and approaches how to make that possible, especially with Java Enterprise and Java EE, Jakarta EE, and Microprofile. So my name is Sebastian Daschner, born and raised in Munich, Germany. And I work for this company called IBM and do a lot of stuff in the Java side and Java Enterprise, so a lot of Java titles involved. And I'm very happy to be back here in Barcelona. Actually, it's one of my favorite cities in Europe, and to talk about this topic especially. And also about myself, what's not on this, the slides, me gusta mucho el café. So this is why I have a coffee shop example, or actually two example applications that I'm going to show you, and where we're going to implement, well, a few resiliency approaches once we run that, either in Docker containers locally or later on in a cloud setting. So what I have is, I want to live code actually most of the time, because I think that's a little bit more interesting than only looking at slides. And I have a coffee shop example. That's a Java EE application, Java E8. And the other application that I'm using is called Barista. So two applications, they're all standalone to microservices if you want. One is called Coffee Shop and the other is called Barista, and they two communicate with each other. And just because I'm brave enough, they run on JDK 12. Who of you uses JDK 12 in production? Hands up. Oh. JDK maybe 11, 10, or 9? Oh, better. Okay, now everybody, JDK 8? Yeah, that's what we know. Okay, anyway. So let's do this. And what I do, just to show you quickly, just let's step through the code, how we, well, can order some coffee. So what I have is some HTTP endpoint, some interface implemented by JAX-RS. JAX-RS, the Java EE standards to implement, well, REST. So that's quite straightforward, but this is what a lot of enterprise projects have. So I have something like /orders. That means I register a resource, a URL /orders, where I can get or post coffee orders. So that means in order to get some coffee, I would request, I would have an HTTP GET request, or for example, I would have a POST request to order some coffee. And that's one of the main paths that we want to look at, because when we order some coffee, imagine we also have to talk to the second backend, the Barista backend. So in this example, that's all synchronous communication that, well, whether you like it or not, that actually matches a lot of the enterprise projects, what they do here. So let's step through this code quickly. We have some component here, coffee shop class, that implements that business logic of ordering a coffee. And part of that business logic is to talk with the other application. So what we're going to have, we have a start coffee brew method on that Barista that is, a client or a gateway class that actually talks to the other system via HTTP, via an HTTP client. How that's done is we have a little bit deeper look in a second. What we have now, that's a terminal, and I have some Docker containers already running. And what I'm doing now, I run my coffee shop application. The Barista application is already running, and we'll talk about this a little bit in a second. So what that is, it's, well, a small wrapper script that uses a tool called watch and deploy, or WAD, that basically, well, listens for file changes and would redeploy my Java Enterprise application to a running application server, in this case Liberty, that runs in a Docker container, just to, well, have this turnaround while developing a little bit shorter and make this a little bit faster to use. And then once that is up and running, what I can do, I can access my application, the coffee shop application, the one that we're going to talk to, with HTTP, with any REST client of our choice, for example, curl. So I can curl my local host, 9080, that runs locally, and can say, coffee shop, that is the default context. And then what I have with this JBCNConf', where is it, configuration, I typically have an application path, something like /resources, and then /orders, right? So let's have a look at that. And then hopefully we have good news, HTTP 200 OK, and this is an empty JSON array, so there is no order in the system, right? And now, in order to change that, what we have to do, well, that's basic, REST, we're gonna post application JSON in this case, or any content type that our application supports to this resource in order to create a coffee. So how does it look like? Do we have a coffee order, and that coffee order in this case, so this is a straightforward declarative mapping using JSONB, again, what a lot of projects would use. And we have a coffee type, for example. So we have an order type. What is that? That is an enum here in this case. For example, we could order, yo quiero un latte or espresso, right? Espresso. We want to order some espresso? Yeah? Okay, let's do that. And then hopefully we get something like successful response 2 or 4, no content. And now apparently, or hopefully, that is, well, first of all, in the system. Okay, this looks good. So we have now an order in our system, and apparently, if you look at the code, that also was communicating with the second backend, right, with the barista backend. Okay, that looks good. We can do this again, and we can order another coffee, and so on and so forth. Now, one thing that we want to talk about is resiliency concepts that should be quite straightforward, but is still not, well, sometimes neglected, are timeouts. Whenever you have synchronous communication, you have to think about at least the concept of timeouts. What does it mean if something could time out in your specific application? So how long do we want to wait for a synchronous request until it's invalid? And the thing is, depending on your implementation of the HTTP clients, so how I created my HTTP client using the JBCNConf' client here is I just say new client, and that uses the default timeout setting. And there are clients out there that actually have infinite timeouts. And I hope I don't have to tell you that this is a really bad idea, right? Because, well, what happens, you would basically block all the threads at some point. So what we're going to do, let me open up, let me ask for a little bit more coffee, more coffee, more coffee, right? Let's just continuously fire some more requests and do this again and again. I'm just ordering a little bit of coffee here. And now what happens is if actually the second backend, well, becomes unavailable, right? If my barista system is not there anymore, so let's just Docker stop that system. Oh, and now as you can see, it doesn't move anymore. So now we're basically running into some timeout situation. Quit coffee shop. And that just, well, makes the whole thing kind of unusable. Because we have a few threads in our system, but at some point we stall all the threads. Okay, what did I just do? Docker kill. What we can actually do for, I think, all of the JVMs, if we send a quit signal, Unix code 3 to a running JVM process, we will dump the core. So we will have a thread dump, or depending on the implementation, and can have a look at the current situation here, in this case, when it comes to threading, for example. The same works in Docker containers. If you say Docker kill, it not just solely kills your container, you can also send different signals. So what we can do, actually, we can have a look into our container and analyze that situation right now, what is happening. Let me go into the coffee shop container, into, I think it's called coffee shop. Yes. What we can do, that runs in my environment here. It's user server, I think, default server. Yes, we have a Java core file that has been created by the OpenJ9 runtime that I'm running. I have Java 12 running on OpenJ9, and these files will be created once you do such a dump. And what we can do, have a look at the threads component, and I think they're called executor. something like this, default executor thread. Yes, default executor. And just a very quick analysis of what we have here. We have multiple threads in that component here that all, well, do a different thing. So this, for example, is, well, currently waiting in a thread pool executor. So that thread is currently, well, doing nothing, is waiting to be utilized. This thread right now is in state runnable. But, well, if you have a look at it, it actually can't run because it entered a log at this point. Plain socket implementation socket connect. If we go down deeper, the stack trace, we'll end up at CXF. Oh, barista send request. This is where the track is, the thread is currently well, stuck. Next thread, socket connect. Okay, same story, stayed runnable, and right now, well, it entered a log. Won't actually continue to do some meaningful work. Barista send request. Looks familiar? Next one. Oh, socket connect. Barista send request. That's the third one, and then the other ones, yeah, are currently waiting in the thread pool, and that's about it. So there's one particular situation, well, how we analyze such a situation, and then of course, well, how to mitigate that is, well, to build in some timeout. In this case, with JAX REST, it can be done with, since JAX REST 2.1, with standardized methods when we create our client, so please don't do this. Do something like this instead with the builder. Once you create some client, what we can do is some socket connect timeout and some read timeout. For example, 3 seconds, just for the sake of the example, whatever makes sense for your particular case. Read timeout and connect timeout, and then build this whole example. And now in our case, what we do actually, thanks to this watch and deploy tool, we will just, well, redeploy the whole story. And Docker run barista. Of course, I have to start my barista backend again to, well, see to have a look at the same situation. And then what happens? I now just redeployed the new code, and then hopefully we won't run into the same, well, situation anymore. So that is true for all synchronous communication that you have. Prime example, HTTP. Same for databases. Whenever you calling something, that something else might actually not respond. So you have to think about that, and it's quite, you know, a business question as well at some point, because it's always the question whether of progress versus, you know, responsiveness of your application. Let's do this again. Docker stop barista. In this case, what you can see, you will also be stuck in this point, but only for, well, 3 seconds in my case, if you're stuck at that socket connect where you're trying to access the backend. So that's to be said about timeouts in this case with that particular example of HTTP clients. In general, what you want to do, you want to have a scenario where you can test all of these different behaviors in different scenarios, like a test harness that you build up as part of your pipeline, and where you actually test all of these situations. Because, well, that might happen in production, right, that your other system is going down, and then you can already see as part of your test scenario how my application reacts to that scenario. All right. Another pattern, resiliency pattern, or what I want to talk about is bulkheads. Bulkheads on regarding threading. So where does that name come from, bulkheads? It actually comes from the ship construction. So why do ships have bulkheads? So what is a bulkhead? A bulkhead is a compartment in a ship, in a constructed ship, or actually multiple compartments. So what happens if your ship hits the iceberg and the hull gets damaged, that your whole ship doesn't sink, because only one or a few of these bulkheads are actually destroyed, and the rest of the ship stays intact, and then you still can make it to the harbor. Fun fact, or maybe not that funny, if you know about the Titanic, actually the Titanic had bulkheads, but apparently they were not high enough or sealed enough. So, well, we all know the end of that story. So outcome is you always want to test your bulkhead and your proper behavior of your application as well. But talking about that, so what is it? What are these multiple compartments that we want to introduce for our application? Well, we might have multiple functionality, or multiple parts of functionalities in our application that if one functionality, for example, gets overutilized or fails for some point, that the rest of the application stays intact and is still usable. So for example, if a user overuses, as in a DDoS attack, one part of the system, that the rest of the system stays intact. And what that means for enterprise applications is typically threading and thread pools. So what I want to show you right now is if, and this is now a similar example, let's shut this down and do something similar. That response on top left is constantly creating new coffee orders. And this down, bottom left, is asking for coffee orders. So that is the get orders, and top left is post orders. And what we have, let's actually speed this up a little bit. What we have here is we're constantly, creating new orders, reading orders, but now I have a fancy script that actually is a load test that hammers our application with a lot of requests. And what you can see here now, same story, I stall basically my system, and then it's not able to, neither read or write new coffee orders until that load test is done. What that means, out of the box, what we have in JAX-RS or in servlets is we have in most of the application implementations a default HTTP request thread pool. A single one. A single request thread pool that is being used where all these threads will actually execute our business logic and are being used to do that. That means we have a single one. Once that is being overutilized and that when it's full or rather empty, then, unlucky, we cannot serve other requests. And as you can see, the whole thing stalls. So actually, all of the requests take much longer. So in this case, as you can see, how to mitigate that? First of all, we want to introduce the notation of bulkheads, like multiple bulkheads. As of that, for example, if the reading functionality of reading new orders, coffee orders, is being overused, that at least we can still create new orders, right? And then as a second notation, we actually can come up with, a better approach of how to define that functionality, especially how to define the queues internally that are being used, and what to do if the system actually is being overloaded. And there's a better notation of, back pressure on the server side that we're going to implement. So it's a nice ASCII art. What we do in our scenario, we have, a thread pool, or in this case, we actually have only a single one. And then, like in an airport security, multiple threads that can handle whatever comes in. Then you have a typical average transaction time. How long does it take to handle that request? And we have so and so many threads in that pool. And also we have a queue where we wait, and the queue is so and so long. You can set a maximum queue size, and then depending on what happens if the queue is full, and of course so and so many requests that are currently sitting in the queue. So there's a thing called queuing theory, and you can imagine, the longer the average transaction time, the longer it takes. The more threads I have in my pool, on average, the less time it takes, and of course the longer my queue, the longer it takes, but also the more requests I can handle until the whole thing overflows. So what I do now, I actually create a notation here in my JAX-RS resource to first of all prevent that we only use that single HTTP request thread pool. And you can use so-called asynchronous JAX-RS resources for that. And since JAX-RS 2.1, there's actually an easy way to define these by just making the resource, the method, returning a completion stage of whatever you want to return. So that means, I'm going to implement that in a second, if we have a completion stage of, for example, coffee order, then this will tell the JAX-RS implementation that we don't want to use the default HTTP thread, but that this will actually get suspended, and that whatever defines the completion stage internally is being used, that thread, to execute the business logic and to, continue the request. And now, what we can do, we can make the coffee shop also return a completion stage. How that works then, or how we create these, is what I will show in a second. You can actually use a microprofile project that works well together with our Java Enterprise application to implement that. And then in our case, what we do, coffee get orders, what is this? Then apply orders.stream. So it's live coding, right? Everything can fail. And I count on you that you call me out if I make coding mistakes, okay? So if something fails, it's your fault also. What we have, completion stage of this, that means we return coffee shop order coffee, and in this case, if the order is successful, then apply response no content, right? Or exceptionally, throw an exception with that if return this and status get message, yes, and that's it. Sorry? I'm missing here? What do I miss? Yeah? Here? Oh, that's right. Thanks. Yeah, my compiler now is happy. Yeah, he pays attention. Awesome. Somebody else now happy? Will work? Okay, good. Okay, so what I just did, I changed the code here to basically use a completion stage, or it will use a completable future internally, to say, okay, call this order coffee and then apply, well, response no content, a JAX REST method, or exceptionally, well, throw an internal server error and add this header, or whatever you want to use, right? That's just Java, well, coding here. And then I have a completion stage, and now how to create this. Because you probably know in Java Enterprise, you're not supposed to start your own threads, right? Because the application container, the application server is supposed to manage the threads for you, for good reasons. But now, if I would do things like, you know, completable future, supply async or stuff like that, well, bad idea for multiple reasons. So what we have, there are actually a few Java Enterprise extensions out there, or in this case, we can use microprofile fault tolerance that has, well, the notation of creating these bulkheads or actually thread pools for us. So what we do now, let's go to our POM.xml, and let's use microprofile fault tolerance API. Nice story about that is also provided, so we can use that without, well, bloating up our deployment artifact if our application container supports it. So I'm using OpenLiberty, which supports both Java EE and microprofile or individual specifications of that. And what we can have is a bulkhead, annotation at bulkhead. And if I combine it with at asynchronous, that both come from microprofile fault tolerance, we can actually define that method as follows with the return type completion stage. And in this case, I can do a thing like completable future, completed future, which sounds like it doesn't really make sense. But once my microprofile implementation sees this, sees the signature, it will actually swap out whatever is being returned with a completion stage or completable future that actually uses a thread pool under the hood. A thread pool that I define using this bulkhead annotation. And then I can specify, for example, what is the value of the thread pool size, basically let's say 4, and what is the length of the queue. And I can do that for all of these methods here, and then I literally specify 3 different bulkheads for these 3 different methods. And then I just say completable future, completed future here, and the same thing down there. And then the compiler is happy. And if I do that, well, I can now actually redeploy. Already doing that. It's building right now. And then it will redeploy this, and hopefully what I can do then is basically rerunning that example, but now using multiple different thread pools. So now it's been redeployed. You saw the quick 404 message. So that works here. And now what I can do, I can rerun the load test. And now what you can see, the whole system stays responsive. And now in this case, on bottom left, I sometimes get a 503 service unavailable error. Why is that the case? Well, because this is how I react to what happens if the queue overflows, right? So that is the default notation. What happens if my bulkhead is basically full, if all the threads are being utilized, and if the queue size is full? Well, what happens internally, it throws an exception, right? You can handle this scenario in multiple ways, but if I have an exception here, I can actually handle that in a JAX2RES exception mapper. And what it does, it has a completion exception and maps that to service unavailable. Why? How does that make sense? So this is the notation of back pressure on the server side, is to say, okay, whatever happens, I want to notify or let the client know that I'm currently under heavy load. And there are multiple approaches to that. And this is a very drastic approach of just saying, okay, error. But in any way, what I want to guarantee, I want to fail eagerly because I can already know or I can calculate that I'm not going to respond within a certain time, right? So that's the whole idea of saying, well, it's better to be predictable and to know whether or not I make it within the SLA, service level agreement, time that I'm supposed to respond in, or fail immediately. So what that means is you can actually calculate and then, depending on that, size the thread pool and the queues following this queuing theory and what is called Little's law by saying, okay, if my thread pool is currently fully being utilized and my queue length is so and so long, that means I can calculate based on transaction time, queue length, and number of threads, whether or not you're going to make it within a certain time. Or in other words, you can size the length of the queue to say if the queue gets longer, that's great that I have more capacity, I can handle more requests at a given time, but also it will take longer, right? Because the queue is longer. Think of an airport security, right? So what I can do, I can limit the queue size and just say, okay, if the queue is full right now, then it will be rejected. But that also means that you're not gonna make it within, let's say, 200 milliseconds or 20 milliseconds, if that is the SLA time that you want to guarantee. So by sizing that system in that way, you can guarantee that you will make it in that 200 milliseconds, and if not, you will be rejected. But the good part is you will be rejected right now, and the client might be able to go to a different system and ask the other system and still make it within that SLA time, right? Because the worst thing you can do is eat up all that SLA time and stall your user and then not even responding to it because you're currently being overloaded. So that's the idea of that, and that's one way how to implement that depending on these numbers in your system. All right, we can run this again if you want. So you see the whole system stays responsive, and if anything, at least the writing new coffee orders is not being overloaded. You always have a successful response here because that load test actually overloads the get orders functionality. So these are the two things. We see that only that bulkhead, that part of the system was under load in this case. And that's one way. There are many ways how to implement that. That's one way with Java Enterprise. What else to be aware of when threading? Again, threads must be managed by the container, so you have to know what you're doing under the hood or which managed thread pools you're using. This fault tolerance is one way how to do that. And then again, regard these the thread pools you have and the queue sizes, and of course that default single HTTP request thread pool. So know how to implement asynchronous JAX-REST responses or whatever implementation you're using with that. Another thing that I quickly want to show is circuit breakers. So that's another resiliency pattern, comes from electrical engineering. That means, before we want to have, or before we have some bigger further damage, we actually want to prevent something to happen, and we rather fail in order to prevent, something that is doomed to fail anyway. So in a house, if the circuit breaker trips, that's bad, and you cannot use your device anymore. But that's better if that is the case, rather than your house burns down. So ideally, we do not expect a circuit breaker to trip in a fully functional system. But if so, then it's better to do that rather than to have bigger damage. There are multiple ways how to implement that. If, for example, you have a circuit breaker that is based upon exceptions, and then you handle these exceptions, and for example count how many you have, and if there's too many, then you just fail eagerly without even calling, without even attempting to call the same functionality, just failing immediately. And then typically after some downtime, you try it again, maybe once or twice, and then if that works or not, you either are then closed, the circuit is closed again, or open immediately again. That means you fail or not. In microprofile fault tolerance, there is also an integration for that. That is called circuit breaker. Quite easy, so matches the Java Enterprise programming patterns, again, declarative approach of just annotating something with, in this case, add circuit breaker. And what we can have is we can further specify, well, how that circuit breaker should behave. For example, we say we have a request volume threshold of, let's say, 10. So that is the current window of the 10 requests we're looking at, or the 10 invocations of that method. And then, for example, we can have a failure ratio that says if more than 30.3 of the 10 requests fail, then the circuit will be open. And it will be open until the delay time of, let's say, 3,000 milliseconds is over, and then it's attempted, then it's half open, then it's attempted to try out the invocation again. Per default, that means failing means any exception that this method produces, and then we will immediately fail or not. Okay, we can do this, and then just for fun, what we can do, we redeploy our application. That's already the case, and then we can actually stop this here. And then what happens? Well, nothing, because it doesn't fail currently, right? It just works. Okay. That means, just for fun, let's create some failure here. If new random next double smaller than this, illegal state exception. Bam. Just because we can. Let's rebuild this and redeploy this quickly. And then we can see, actually, once that has been redeployed, we might have, let me search for the error actually. So depending on whether we're lucky or not, we get an error. Okay. And if we have too many errors in the last 10 requests, well, then you can see we have, make this a little bit faster. We have a circuit breaker open exception. So that means that now the circuit breaker is open and it doesn't even attempt to call that method anymore. And then when it's half closed again, then you see if the first request or the first invocation works or not, then it will be closed or open again. So this is one way. Let's now get rid of this code again. How to implement this using a microprofile fault tolerance. What it can also do for all of these fault tolerance guarded methods is to specify a fallback mechanism with another annotation where it can point to a fallback handler or to a method in the same class to say, okay, if anything happens, that means if the bulkhead is currently overloaded, or if the circuit breaker trips, or there are a few other things, there's actually also a timeout annotation here, then we can point to that fallback mechanism, and that will be executed instead. So that's another way how to do that. What else is interesting? There is actually a Grafana dashboard available for microprofile fault tolerance. If you use microprofile metrics as well, that integrates quite nicely. Have a look at, just 1 second, at the server configuration. So that is now specific to, in this case, I'm using OpenLiberty. And what you can do, you can use, for example, microprofile, what I have here, metrics and fault tolerance, this combination. So that works then that you have a metrics for Prometheus in this case, where you can have some more, where is our We can have some more information of the bulkhead, for example. So what is the current call size and stuff like that. It comes out of the box if you use this with metrics. All right. Then what else is there? In general, what you should do is to build up a test harness for your application. That means all of these things and many, many more of these concepts that can fail in production should be tested within your test scenario. That means if you build up such a concept and make it part of your delivery pipeline, you're actually refining and hardening your application and the whole process more and more, right? Because if anything happens in your production environment, you can actually write a test for it. Think about these timeouts or circuit breaker behavior, what happens if something fails, and then you can see how your application reacts to it. You should test your database connection behavior as well. Same story like timeouts. What happens if the database goes down? Does it come back up again? And does all of that work? Test data marshalling and all the communication using protocols such as HTTP, for example. Well, should also be tested, and you should see how your application reacts to, for example, if there are any changes in a data format, just to make it more responsive to change and to implement that more resilient. Extensive logging, well, that's a whole topic on its own. Short answer, just avoid to log, especially extensively. Well, that's another topic here. What else I want to show you quickly that goes a little bit more into cloud technology is, first of all, container orchestration, and then we quickly have a look into service meshes and Istio, because, well, these new environments and cloud native technologies enable us to build some more resiliency into the whole enterprise system that we have, specifically things like container orchestration. So who of you knows Kubernetes? Hands up. Quite a few of you, okay. So I quickly want to show, do we have this rolled back up again? Yeah. Kubernetes, what we have here. So Kubernetes is one way to run our applications in production, especially in a containerized environment. So what it promises is this one, production grade container orchestration. So we're going to orchestrate all of these containers in our clusters and in all the nodes that we have, right? So that's already a nice story. I have a Kubernetes cluster right here that also has my barista and coffee shop application. So I deployed that I use the IBM Cloud or any Kubernetes environment of your choice. You can have either a hosted version or like Minikube on your laptop to try that out. So what I quickly want to show, let's access this application and have some more concepts here in Kubernetes and Istio. Or actually, before I access that, a few things that Kubernetes already introduces in order to be production grade. So for example, you have a few controllers and mechanisms in place that try to make sure that whatever you specify always will be fulfilled. So for example, if I say, okay, there is a pod, and that pod is my running application that has a Docker container inside. What happens if I now am very mean and say, please delete this coffee shop pod here? Okay, then the pod will be deleted. That's too bad, right? Then our application is down. Well, the nice story is what Kubernetes does, it tries to always make sure that this desired state of having, a coffee shop pod available is always be fulfilled. So it will immediately go and say, oh, we don't have a pod right now, let's better create one again, right? So if something fails, if your application crashes, it will be restarted. A lot of things like that. That's already good news. And then if that's available, well, you can actually access this as well. Let me try out the IP address, find out the IP address of my cluster, and then we have coffee shop resources orders again, right? If that is then up and running. Service unavailable, yes, it's currently starting up. And then, we can access our application in a cluster. What else we have here is a service mesh. So the cluster that I'm running is actually not only using Kubernetes, but also Istio. I know here in this conference there have been a few talks on Istio in general. What that is, well, a service mesh technology is basically a mesh of interconnected microservice deployments where we use proxy sidecar containers that are deployed alongside our normal application container that implements a few concerns. For example, resiliency or some more advanced traffic management. So what we can actually do, we can implement a few of the resiliency concepts on the service mesh environment level already when it comes to networking, for example. So all the connections, like HTTP requests, well, can already implement a few of these concerns. So, okay, now it's up and running. Let's order some coffee here in this environment, cloud coffee. Let's create some coffee here, create some coffee. Okay, that works. Now what happens if actually our application would not implement timeouts like I just did? And there are a few examples for this. So for example, we could have timeouts, we can have at least connection-based bulkheads as well. What I quickly want to show you is the routing here of the coffee shop and the barista. So if you're not familiar with this Istio, this is basically how you configure the routing rules and how the Envoy proxies that work under the hood are connected. What I can do, I can, for example, specify a timeout here. So I can take this route that is basically, well, an arrow in the diagram of how my services are connected. And that means if somewhere from outside of the system somebody calls my coffee shop system, this connection will now have a HTTP timeout of 1 second. Okay. How's that implemented? If you have a look at some more ASCII art here, at the pod, for example, a client pod inside the cluster that would access another service, such as a coffee shop, my main application is deployed alongside with a proxy sidecar container where the Istio pilot component makes sure that this proxy is configured appropriately and where the actual connection is being enhanced with some more resiliency, where the proxy implements some outlier detection, timeout, other resiliency concepts, retries, things like that. All, of course, connection-based, typically HTTP on these. So that means if I specify a timeout here, by the way, who likes YAML, the YAML file format? Hands up. Yeah, a few of you. So that's one example why I'm not quite a big fan of that. Who knows whether this is correct? Or this is correct? Or this is correct? We were talking about markup languages before, but yeah, that's one problem I always had. Okay, anyway. Let's again ask for some more coffee here. And where is my other terminal? Now what I'm going to do, I'm going to apply these changes of coffee shop deployment. And then hopefully, well, I reconfigure the virtual service of having, a timeout specification now. Well, looks good, right? It works. Well, we don't know. Again, we should test that behavior, right? So apparently I just specified for the coffee shop virtual service to define a timeout behavior of 1 second, but well, how to test that? Well, I could, again, shut down my barista application, or I could redeploy it with some, like test flag. If this or that, then make the connection slower or wait for a little bit. Or the good news is Istio also, for testing purposes, allows us to make connections faulty, which actually works very well here if you want to test something. So we can introduce fault notations and have something like a delay. For example, we can have a fixed delay of, let's say, 3 seconds. But not all the time, only in, let's say, I don't know, 30% of the cases. Again, for testing purposes, don't do that in production. What we can do, we can tell the proxy to, well, mess up our connection here on purpose, for fun. So at some point, either our request goes through, or it will wait. Well, in this case, not for 3 seconds, but for 1 second. It would time out the connection there. Oh, by the way, this other error is now our circuit breaker firing. But in this case, we have the gateway timeout from the first connection from the proxy. So again, same story. You want to test, undo this again. You want to test your timeout behavior. And that service mesh is actually a good way to test the resiliency. Because in the same way, you could throw HTTP errors and things like that. So if you have a distributed system, that's a very nice way to just interject and mess up everything that you're doing in your test environment. Another thing that is quite helpful in your whole, in the whole way how you deliver applications and how you deploy in terms of continuous delivery and things like that, is that you can use service meshes to have some more traffic management to, for example, not only deploy in a big bang, but to have something like more gradual deployments, like canary releases, things like that. So actually what we can do, we can tell the service mesh that we want to have. Let's go to the deployment that we, coffee shop deployment canary, that we want to have, for example, a canary release of my application here. Let's go for, I think the health check introduces the notation of, yes, an app version. Let's grab for this. App version. And then what we can do, we can actually deploy something here using deploy v1. Using, in this case, I prepared a script to basically change the notation of how much traffic we want to route to version A and version B. But that is doable using the service mesh technology to, for example, in this case, implement canary releases. So let's say we watching the pods that we currently have in the system. So now we have v1 pod, a new version of that that's currently being started up. And what we can do then, we can run such a deployment and then gradually deploy from, let's say, 5% of the traffic to deploy the new version to 10% and gradually increase that, where at the same time we might have a look at our monitoring in our system. That is actually also comes out of the box with Istio here, and have a look at whether or not the new version, immediately fails. And if that is the case, then at least we only impact the 5% of the user, the 5% of the traffic in that production environment, and not, all of them. So we can actually now delete deployment. Coffee shop. We can delete the old deployment, and then what we can do, we can roll out the canary version of new version v2, and then let's speed this up a little bit. What happens then, it will fire up a new deployment here, and then it will gradually change that traffic from like 0% to 5% and gradually increase that until we route all of the traffic to the new version. So by doing so, you prevent a big bang deployment. Let's see, it's now waiting to be started up. And then if you have any errors, you can quickly roll back, and actually also roll back in an automated way. So while we're waiting on that, we can actually see stop. We can port forward the monitoring here and have a quick look at the monitoring in our system. Port forward Grafana. So this is actually the monitoring now that comes with Istio. Oh, now you can see, now that's been up and running, and what it does, it gradually ramps up the traffic that we have for the new version, and you can see that gradually get more and more responses of the newer version. So that is one way how to implement that. And then in the monitoring solution, you can also have a look at these service dashboards, for example, that come out of the box, and then see how the traffic actually is being routed here. So we see that this was the old version, and then you ramp up the new version and things like that. And by including that with, for example, error detection, you can then automatically roll back and make sure that your whole setup is being more resilient. So let's get to this one. As a takeaway, please consider these resiliency concepts that we saw here, and know what your implementation is doing, whether it's the JVM that you have, what we saw in the beginning, or the application server here. And always have automated processes in place how to analyze and then, of course, mitigate these situations. Things like, how to do the core dump of my JVM and have an automated process to get that faster, or have a proper process how to deploy to a production setting. And by automating that, and by including proper tests, by having some mitigation of if something goes wrong, you make your system more and more resilient and more stable. So that's the notation of continuous improvement. By doing so, I think you can create a really bulletproof system in that sense. So I hope that was helpful. Thanks a lot for your attention.